Okay, so now that we understand a little bit better about how to use the exponential with bases other than e, now I'm going to see if I can work again on page 293 still. Let's see if we can play number 112. Number 112 says, in a protected environment, the population P, so P represents the population, of certain endangered species recovers over time t. So t is given to be time. So write the information down as you receive it. So capital P represents population, t represents time, and time is in years. Now, I don't think it doesn't happen in this particular problem, and I certainly won't try to do this. But remember, if time is given in years, suppose in the problem it says 6 months, then you don't use t equals 6. You use t equal 0.5. So if time is given in years, make sure that anything you use is in that unit. Okay, so population, time, and then again, we're given all of these models will be given to you explicitly. P of t is equal to 30 times, and I'm going to put this in parentheses just to emphasize that, 1.149 raised to the power. My textbook says x, that's got to be a typo. And this needs to be a t. In my text, this says x, it should be a t. And I don't know what that has in your electronic version, but this needs to be t, not x, because this is a function of time. All right? All right, so we're given that. Part A. What is the size of the population? Oh, it says, what is the size of the initial population? All right. Now, most of you have probably been in some sort of a physics class, or you will be in some sort of a physics class. And the thing to know about the word initial, the word initial in this and similar contexts means time zero. Initial is code for time zero. So if you're asked for the initial population, you want the population when time is zero. So what is the size of the population? What is the size of the population? So find P when time is given to be zero. And again, we're given P of t, 30 times 1.149 raised to the t power. And that needs to go in here. 1.149 raised to the 0 power. Now you can use a calculator if you want to. Most of us should know this. We know any non-zero raised to the 0 power is 1. But just for practice, if I have 1.149 raised to the power 0, that stinking better give me 1, and sure enough, there it is. There's my 1. So this one is straightforward. This is 30 times 1. It's 30. And this is population of the certain species, whatever the animal or whatever the organism is. So this is 30. All right? Let's see if we can play part B. Part B says, what is the population, or what will the population be in 5 years? Well, 5 years, t is equal to 5. What will the population be? Find p when t equals 5. So again, here's the model. I want p of 5, and that's 30 times 1.149 raised to the power 5. So I need 1.149 raised to the 5th power, 1.149 raised to the power 5. And that gives me 2.0026. So this is 30 times 2.0026 approximately. So if I multiply that value, again, leave all the decimal string in the machine, take that times the initial 30, that produces 60.08, rounding to 2 decimals. Now, one small detail, this model is counting the number of organisms, the population of whatever species this is. So in this particular case, the population is going to be in whole numbers. That is not a big deal for us, but for the record, if you want your answers to match textbook models, this is in whole numbers because the number of, I have no idea what this model is representing. Let's suppose it represents rabbits. The population, you cannot have 60.08 rabbits. And so in very often in models like this where you're counting the number of organisms, any value you get will be rounded. In this case, we can round 60.08. We can round that to 60 organisms. This is not required for our work, but for the record, that's the value. Technically, this is an approximation. This model is an approximation, strictly speaking, of the population present.